Hello, everyone, and welcome to today's webinar. My name is Lauren Perry, and I'm a Syngap parent and operations manager at SRF. Our presentation today is Brain Banking and the Hispano-American Brain Bank for Neurodevelopmental Disorders. I have the pleasure to introduce today's speaker, Dr. Veronica Martinez-Sardeno. Dr. Martinez-Sardeno is a professor of pathology at Campus Scholar at UC Davis. She received her BS in biology with a minor in general biology and major in laboratory medicine at Complutense University in Madrid, Spain in '98. From 2002 to 2004, Dr. Martinez-Sardeno completed postdoctoral training in developmental neuroscience at Columbia University in New York, and also at the Institute for Regenerative Medicine, Developmental Neuroscience, and Stem Cells at UC San Francisco from 2004 to 2007. Her final year of postdoctoral training from 2007 to 2008 was at UC Davis, the Mind Institute, to include an autism research training program. A recorded version of this webinar will be available on the SRF website under webinars on the family menu. And at the end of the presentation, you will have the opportunity to get answers to your questions, and we'd love to hear from you. You can write the answers in your questions in the Q&A, and we'll answer. And for those of you just joining us, welcome. And again, our speaker today is Dr. Veronica Martinez-Sardeno, and her presentation today is Brain Banking and the Hispano-American Brain Bank for Neurodevelopmental Disorders. And it's now my pleasure to turn it over to you.
Thank you so much, Lauren and Olga, for giving me the opportunity to be here with you today. So I'm going to talk a little bit about brain banking, what it means, and what we do in our brain bank. So as you know, when you study a condition, for example, autism, right, you can do different kind of research. You can do research in diagnosis, you can do research in treatment, you can do genetics, you can do epigenetics, biochemistry, and anatomy, for example. But to do most of these kind of research, like genetics in human or anatomy, you need the brain of the people who suffer from these conditions, right? From these conditions or neurodevelopment. And for that, the way to obtain these brains is to have brain banks. And this is a very difficult thing to do because first you need to have a group of people who is interested in helping research. And then of course you need to have people signing for the brain bank. And unfortunately, some people need to pass away and then donate the brain to be able to contribute to the research. So when I started as a researcher several years ago, I really wanted to study the anatomy of autism. This means how is the brain of the people with autism, how is different from those brains with people who are typical, neurotypical. And my surprise was that first of all, we didn't know hardly anything about the brain with autism. And second, that one of the reasons why we couldn't learn anything about this brain is because there was not enough brains to study. So I decided to start collecting brains to be able to do research in my lab, in other labs, also in other labs around the world. So I started here in the University of California in Davis, collecting brain of people with fragile legs, that as you know is the monogenic form of autism that is most common, and related conditions, for example, fragile tremor ataxia, and also neurotypical brains, because as I say, you need to compare the brain with the condition with the neurotypical brain. If you don't have neurotypical brain, you cannot know what is different in the brain with a condition. So it's very important that neurotypical people donate too. So I started here like 12, 13 years ago, collecting this brain. And then I decided that in the case of the brains with autism, I wasn't collecting enough brains here in the United States, in the area of California. So I decided to expand my effort to other areas. And thanks to my connection with one of the researchers in Hispanic countries, I thought that maybe it would be an idea to ask for help to these researchers. And this is important one because we are able to get brains from there, but also because they are brains of underrepresented minorities. So, you know, here in the United States, it's a country that is very diverse, but one of the problems that we have when we are gonna do research is that most of the brains that are donated are from white people. So there is not so many Hispanic brains, there is no Black brains, there is not other ethnicities or races brain. And I think that this is very important in case some of the differences that we have in the brain that has happened to other medical conditions may differ between races and ethnicity. So we put together several notes. We are working in Mexico, we are working in Colombia, and Puerto Rico, and what we do is to try to gather brains data. This brain bank that we call the Hispano-American Brain Bank on Neurodevelopmental Disorders has several functions. One is brain banking, that is the main functions, but we also promote research among different sites in different countries. We promote teaching, so we do events, outreach events where we teach people about the importance of brain donation and also about neuroscience and neurodevelopmental disorders. And then we do also outreach activities and also education of students that work in the different labs that are part of this project. And as I say, we are working in California, Mexico, Puerto Rico, Colombia, and Dominicana, and also we have people in the University of Pennsylvania helping. And this is how the brain bank works. We normally have a director, and we have also a set of advisors that are people who help us to run the brain bank. And then each country is divided in two sections. One is the section of pathology, another is a section of clinics. So the clinician and the pathologists, the directors have their own team. Then what the clinicians do is to be in contact with the family and to identify donations. And when the donations have been performed, is then the pathology group that take over, and it helps for the extraction and the preservation of the brain. And this is exactly how we work. So we have a donation, right? The clinical group inform us about this donation, and we enter in contact with the family. And then the first thing is we do a series of paperwork where we get an informed consent for donation. Then we obtain the tissue, but we also obtain medical records of the donor, so we can correlate the scientific future findings with the clinical history and the different symptomatology of this person. Then we have to confirm the donation by the coordinating donation group. And what this group does is to find a pathologist of a dinner that is able to extract the brain. So the brain is extracted or in the hospital when the person passes away, on the funeral home, or the body is transported to a university where the brain can be removed. So one important step is to find the person who's going to remove the brain, to find the place when the brain is going to be removed, and to take care of the transportation of the body and the brain. And once we remove the brain, we do it in a very aesthetic way, so you cannot know that the brain has been extracted. And once we have the brain, we divide it in two hemispheres, the right and the left, and one is frozen and the other is fixed. And this is different ways to preserve the brain. And depending how you preserve the brain, you are going to be able to perform one kind of studies or other kind of studies. For example, for genetic studies, for studies of the genes or of the proteins or for the messengers, you need that the tissue is frozen, is preserved like it was in the brain. But for other type of studies, for example, for anatomical studies, histological studies, you need to fix the brain. You need to put it in a solution that is gonna keep the brain in the same way that that it was when you obtain it, and then you can do your study. So we use the brains for our own research in my laboratory, but on the other laboratories from the sites or in the brain bank, but we also donate tissue to everywhere free of cost. And we have collaborated with many countries in Europe, with Africa, Australia, Israel. So we really disseminate our tissue. And this, when you donate a brain, this brain is not going to be included in one project, but it's going to be included in many projects. Why? Because each research group study different parts of the brain. So if, for example, if a research group study the prefrontal cortex, we are going to share with them only the prefrontal cortex, and the rest of the brain is going to be kept in the brain bank for the future studies. So one brain, one donation can be part of many projects. And not only at the moment of donation, but it's going to be preserved for many years. And every time that a new project starts, you know, it will have the opportunity to participate in this new project. So when we have the brain well preserved, we do what we call the postmortem diagnosis confirmation. So since we are getting brains from the whole United States and also from other countries, the way that we have to diagnose the disease is different. For example, in the case of autism, are not the same that behavioral tests that are performed in Mexico that they are performed in California. So what we need to do is to unify the diagnosis. We have the diagnosis that the brain comes with, but we also do our own diagnosis. And we do this with a test that is called the IDR, or Autism Diagnosis Interview Revised. That is a series of questions, around 150 questions, that are performed to the parents or the siblings or the family or the caretakers of the donor. And with this, we unify the diagnosis, and this is part of the package that was with the tissue. So once we have the brain tissue and the clinical history all complete, this is the resource that we offer. And when a researcher approaches us and they ask us for tissue, what we do is first to ask them about what kind of research they are going to do, and when we are sure that it's like a proper petition and real researchers, we approve the project, and then we donate the tissue. And then we keep in contact with investigators because we know to talk, we want to see how they are doing, if they need anything else, and be sure that the tissue is used for the research, and we are aware of the results of the research. So, and that's really how we work. And today, since we have some time, what I want to give to you is an example of a project that we can perform with tissue in this research. And today I'm going to talk about the brain with autism, so to give you an idea how this research is performed. So in the cerebral cortex, the outermost part of the cortex of the brain in humans, there is excitatory and inhibitory signals, and this needs to be in a balance, and this balance is necessary to keep the proper functioning of the brain. So we know that in autism and other neurodevelopmental disorders, this balance is altered. And we know this because when we do an electroencephalogram, an EEG, the waves that you see there are altered. And these waves are the summative of all the signals that are taking place in the brain in a given time. So then what can be wrong when this balance is altered? Well, it can be that the excitatory signals are altered, that the inhibitory signals are altered, or both signals are altered. And why one of these excitatory or inhibitory signals will be changed? Well, it will be changed because the number of cells that are excitatory or inhibitory are changed, or because they are there, the same number, but they are functioning different, or probably both of the cases. So how we research that? So we take a brain, this is one of the donated brains, and we look in the brain the area of interest. This is the area that we want to study. And the brain is divided in many areas, around 150, and the areas that we have studied are area 9, 46, and 47. And we chose those areas because they are areas that we know are relating with functions that are altered in autism. The area 9 and the area 46 They are in charge of working on spatial memory, verbal fluency, auditory, and verbal attention, while the area 47 is in charge of oral and sign language. So what we do is to cut a slice of the brain that you can see here on the side where you have our areas that we want to study, area 9, 45, and 47. And then we take these little areas and we cut them, we cut a little block, and we put the block in a machine that is able to cut very thin slices of brain. And when I mean thin, is really, really very thin. They are like, they can be like 20 micrometers thick or 10 micrometers thick. That is like a portion of a millimeter. So it's very, very thin. And this allows them to detect proteins. And this is how we see when we put this slide in the microscope, this is what we see. And in this case, what we are studying are interneurons. Remember that I told you that the cerebral cortex has excitatory neurons that are called pyramidal neurons that have a positive signal, and then we have inhibitory neurons that have a negative signal, okay? So we know that in autism, some studies that we have done and other people, we have seen that there is more excitatory neurons, but nobody has ever studied inhibitory neurons, and that's why we decided to study this. So what we did, and these inhibitory neurons or interneurons are called, you can see that they are labeled here in different colors. So there is different kinds. There is up to 20 kinds of interneurons. So since there is so many, what we did is to group them in 3 groups and we design a method. So each group that you can see has a different color, and we can call them the pink group, the blue, and the brown groups of interneurons. And then once we did this in different regions of the cortex of different patients, both with autism and neurotypical, then we quantify the cells. And we do this with a microscope that is connected to a computer. So this is a reconstruction. This is a piece of cortex, like the image that I showed you before. And then in the microscope, we are able to map the different kind of cells. In this case, the pink, the brown, and the blue. And this is how you see the different areas, 46, 47, and 9 in the control tissue, neurotypical, and in the tissue with autism. And then we count them. And when we count them, we saw, here you can see in this graphic, this is the control cases. There is around 10 cases of control and 10 cases of autism. So you see the control has an amount of cells for each case, and for autism the same. But in general, when you apply the statistics, you see that there is a significant decrease of the number of pink cells in this case, and in autism when compared to the control. But there is no decrease in the number of blue cells or in the number of brown cells. So you can see here in these graphics that the decrease in the number of pink cells, that in this case they are called parvalbumin cells, because are cells that contain this protein, parvalbumin. So these parvalbumin cells that we see in pink in this case, they are decreased between 60 or 70% in the area 46, around 40% in area 47, and around 40% in area 9. So there is something different. And it's very unique because we only found them so we only found differences for these cells, for the parvalbumin cells, but not for the other cells that we studied. And what is their cells? What are these parvalbumin cells? Well, these parvalbumin cells are called chandelier, and they are called chandelier because they look like a chandelier of those that hang from the ceiling, like this one here in the image. This is the real cell. This is a chandelier cell or a parvalbumin interneuron cell from a mouse. So the interesting thing in mouse, you can apply techniques that you cannot apply in human, because the tissue that we have in human is post-mortem, but we can label in the alive animal in mouse. So we always want to see more, be able to apply more techniques in animals, but at the same time, the animals are not human and they don't have the same brain. So both animal studies and also human studies are very important to understand its condition. So as I was saying, this is a chandelier cell in human, and you see in green and in red different parts of the cell. So these cells is very interesting because all the interneurons in the cortex, normally the synapse, so they send the signal from a structure that is called into a structure that is called dendrite in the pyramidal cells. So we have the inhibitory cells, the negative cells that send the signal synapse into the excitatory cells that are the pyramidal cells. And you can see a skin here. You have here a pyramidal cell or excitatory cell that is called pyramid because has it looks like a pyramid, right? And then you have all the interneurons or inhibitory cells sending signal into this other cell. So the interneurons, the inhibitory, are controlling the excitatory signal in the pyramidal cell. So this channel cells is very interesting because instead to controlling the pyramidal cells through the dendrites, is controlling the pyramidal cells through the axon. And the axon, the dendrites normally receive information and the axon send information to other parts of the cortex or other parts of the brain. So this cell is very important. This cell is very important also because while a regular interneuron is contacting one or two pyramidal cells, this interneuron, the Chandler cell, is contacting like 200, 300 pyramidal cells. So it's like one single neuron has a huge effect in many other excitatory cells. So you can imagine if you lose one of these Chandler cells, you are going to be losing the control over many, many pyramidal cells. And this is just when I see you a real picture of a Chandler cell in a human and a reconstruction. And well, the Chandler cell, what it has is an axon. The axon transmits the signal that is very, very big, different from the other cells. And they have these terminations that are in red here. And you can see here also in C and D, you can see the terminations in human and high magnification. And when you look at high magnification, you see that there is little balls, and these balls is where the signal is transmitted. So when we study these balls in human, is that in the cases of those people that have autism, these balls are smaller. And this means that they are less likely to transmit a signal. So far we are seeing that there is less Chandler cells, and those that are there have a smaller synaptic site, smaller balls that are the areas where the signal is transmitted. And you can see here the graphic depicting the size of the different buttons or bolts in each of the cases, and a little dot is a case. Okay, so other thing that we study is, okay, we have these cells and they synapse into the pyramidal cells and they send a signal, and the signal is a neurotransmitter. So it's a protein that is released and then binds to a receptor in the target cell. So this receptor, it's called GABA alpha 2, and it's in the axon of the pyramidal cell. So we studied the amount of this receptor, and we saw here is here in yellow in neurotypical, and this is how a case with autism looks like in yellow. So what we saw is that the amount of this receptor is decreased also in cases with autism. And you can see how it looks like here, the different amounts of the receptor. So this was just a little example of how we can find anatomical changes in the brain using these tissues that are donated. So the summary so far is that I tell you is that we have found less Chandler cells that are inhibitory cells and are cells that are synapsing in excitatory cells. They are, since they are inhibitory, they are like inhibiting the excitatory signal from the pyramidal cell, and therefore the brain is getting hyperexcited. That is what is happening in autism, that the brains are hyperexcited. We also find that the Chandler synaptic buttons that are the place where the synapses of the signal take place are smaller in autism. And we also found that the amount of GABA receptor, that is the receptor that bind to neurotransmitter, to the inhibitory neurotransmitter secreted by the Chandler cell is also decreasing autism. So, and one other thing that you can do, remember I told you when you donate a brain, we have the brain, and then we have the clinical history associated. So one thing that you can do is to take all this data that we have collected. The data that I give you is a very small summary of everything that we found, but as an example, but we can take all this data and we can correlate it with the behavior of the person. And for that, we remember that I told you that we did the IDR, that is a test that you do to the parents or caregivers of the donors. And in the case of autism, this test look for 3 domains. One, the 4th domain is just that the symptoms need to appear before the 36 months of age. But for then there is other 3 domains, A, B, and C. The A is a series of questions that are measuring qualitative abnormalities in reciprocal social interaction. The B is looking for abnormalities in communication, and the C is looking into restrictive, repetitive, and stereotype behaviors. Okay, and then each domain, for example, the domain A, qualitative abnormalities in reciprocal social interaction, have subdomains, A1, A2, A3, A4. For example, A1 is failure to use nonverbal behavior to regulate social interaction. And each subdomain, in this case A1, has several questions that in this case are question 50, 51, and 57. And the same for all the domains, for all the subdomains. And there is a total of 150 questions. So the parents, they just answer all the questions and we put together all the domain. And then what we do is we have a statistician who takes all the anatomical data and histological data, all the clinical data, and does a statistical correlation. And I'm gonna tell you we have found related to the data that I showed you before. So what we found is that the Chandler cell decrease, the decreasing number is linked to the restrictive repetitive behaviors that are typical in autism. And here you can see the numbers, again, like I showed you before, the reconstruction of the cortex with different type of cells, right? And you can see here how the neurotypical case of control looks like, the cortex. You can look at the parvalbumin cells are the blue cells that you can see them here in the low panel. And do you see when the value C3, that is the core in the domain 3, subdomain 3, C3, you see how the number of cells look like when C3 equal to 2, the number of cells decrease. When C equal to 3 or 4, the number of the cells decrease more. And this, the C3, is the subdomain that is related to stereotypical motor mannerism. So we have able to link this type, the decrease in the type of cell, to a subdomain of behavior. So the domain will be the restricted repetitive behavior, and the subdomain will be the motor, what is called motor mannerism. Okay, so you can do a similar analysis with all the conditions that you study, and like this you can assign a behavior to an anatomical alteration. This is similar, so that when we do an experiment, we always do the experiment in different ways. So in the previous, we were counting number of cells. In this one, we are counting number of cartridges and buttons. That is the place where the synapses takes place. And we see the same. We see using different methods and different results, but they are related. We find also that there is a correlation with the C3. And also this research is done by different, not only different methods, but also by different researchers. So we are sure that our results are real and they don't have any bias. Okay, and then we see here, for example, the reconstruction is made in other way, the amount of cartridges in neurotypical, and when C3 is equal 0, 2, 3, and 4, the number of cartridges decrease. So this is indicating it's a different way to arrive to the same result that I just saw. So the result that we found is that, as you know, autism sometimes comes together with intellectual disability. So when we found that the histology or the anatomy is different in the cases that only have autism versus the cases that have autism with intellectual disability. It's like a different condition. So far we were studying autism, and in autism we saw that only the parvalbumin cells were decreased, the Chandler cells. But when we study the cases that in addition to autism have intellectual disability, we see that in addition to the parvalbumin cells, other type of inhibitory cells are also decreased. So as you see here, the cells are depicted. When before I saw you, I think pink, blue, and brown, but here is, we just gave in different color, blue, black, and white. So anyway, the point here is that all the cells are decreased, and this is where it produced the intellectual disability. And this is just a representation of the different kind of cells and how they decrease. So I think that what I have shown you in this short talk is just that Chandler cells are decreasing autism, and that this decrease is related to if it's generalized. So in addition to the Chandler cell, other interneurons are decreasing number. This is related with intellectual delay. And we also saw that the decrease in Chandler cell proper is related to stereotypic motor behaviors. And this is very interesting because in schizophrenia, there is a condition that shares this same behavior. We have also seen, other researchers have seen that there is also a decrease in Chandler cells. So I think that this is interesting. So overall, I show you a little bit how brain bank works. I show you that an example of a study, a histological study, anatomical study in autism, and also how this allows you to relate it to stereotypical behavior. And when this kind of research progress, because we have more tissue, and since once you have more tissue, you have more research projects, and even more researchers that dedicate themselves to study this kind of problem, then we will be able to discover things that will help us to understand the condition and to establish treatments, and also to try to establish treatments, and I'm sorry, I'm lacking out in the word, to prevent comorbidities associated to the disease. And I just want to say thank you to my team. This is my team that are the people who made this kind of studies possible. Thank you so much, everybody. Thank you.
Thank you. That's great. So much. We have Dr. Schlecht here. He has his hand raised if he wants to ask a question. I'm let you speak, Hans, if you want.
Yeah, thanks very much, Lauren, and thank you, Dr. Martinez Cedeno. So I'm a big proponent of brain donation. I realize it's not the most palatable subject. I think it was one of the strangest experiences I had in life to sign up. You know, my son, going back now 5 years ago, for his donation, and then more recently my own donation, so that we can go as a pair. And even before my son's diagnosis, it was the New England Journal of Medicine paper on an autism brain pathology study. I guess it's probably from 10 years ago now, where, you know, they demonstrated sort of the cortical disorganization within the brains of kids and adults with autism. And it's really impressive because, you know, that was at least a way to tie together what happens in humans to what is seen in the animals and the animal models of autism. So it was really an impactful paper, and brain donation made that possible.
Yep.
You know, for the layperson, I don't know if you touched upon it. I had a meeting, but missed it in the first few minutes. But I think people are worried that there could be, you know, an inability to have their normal funeral practices if they donate a brain. Can you make a comment on that? You know, is an open casket still an option?
Yes. I mean, when there is a donation, the donation is done very fast, and most of the times people call us before the person pass away, so we are ready. And this is very important because when the brain dies, you need to preserve it as close as possible to how it is in life, because you start losing properties and it's more difficult to do study. So the procedure is done very fast and it's very aesthetic. So you cannot see absolutely anything. I mean, you cannot know that the donation has taken place. And all the process after that it's normal. So the people who do that is very professional, and normally there is not any kind of change in time or any of the process that the family goes through. I mean, it's very difficult. It's a very difficult decision, and we understand and that's why it's so difficult to have brains for donation. But it doesn't affect in any way the process, the funeral or any of that.
Fantastic.
Did you say how soon you needed them? I might have missed that detail.
Well, we need it as soon as possible. There is time that the person we know that is gonna pass away and we are ready and we collect the brain 2 hours after death, Other times it's not possible. Mainly in these countries, in other countries, in California, it's faster because we have all this infrastructure and technology and people who can do that. But in other countries, perhaps it takes longer time. Anyway, every time there is a donation, we try to do the fastest as possible, but if it's not very fast, we still get the brain, because even if we cannot apply all the techniques, we still can do some, and it's so invaluable, the donation. I mean, every brain is like a treasure.
Yeah.
So this is what we try to do our best.
Yeah. Well, do you have any other questions, Hans, at all, or any comments?
No, I'm all set. It's just fantastic.
It
Also
is.
for an outreach to, the non-traditional research patient, right? So, when I was practicing in HIV and infectious diseases medicine, most of the papers were 90% men and 90% white men.
Exactly.
And that did not reflect the patients I was providing care to in downtown Philadelphia or Springfield, Massachusetts, or Boston, pretty close, but not necessarily. And there has to be a level of diversity to science so that there is a generalizability to the patients that we see. So I give you all the credit for putting in what's probably an incredible amount of effort to make this happen and involve a community that is not part of the routine and research.
Yeah, what you say is absolutely true. It's men and white, like 90%. And I don't know why. I think that the men brains are donated by their wives, so the wives are more likely to donate, but the men are less likely to donate, so they don't donate their wives' brains. This is the only thing that I can think why there is a gender difference. Race and ethnicity makes sense because it's related with access, to this information. And also in the Hispanic and Black community, there is still a lot of, it's still very hard for them to donate due to culture, at least in the Hispanic population. So that's why we do a lot of outreach programs, trying to educate and trying to give more information about how important is this. And it's difficult in the United States, but most difficult in the Hispanic countries. And in the Hispanic countries, where we are obtaining is not only Hispanic country, but we are in the Dominican Republic, that there is a lot of African-American countries, and also in the north of Colombia, also we have a population that also donate African-American brains. But as I said, we try to do as diverse as possible. It's a huge amount of work and not always work, so we are very slow, but at least we are trying. I think that is the message. We are trying.
Yeah. Super. Congratulations.
Thank you.
Thank you, Dr. Martinez-Cedeno. This has been very interesting. I have a couple of questions before we finish up. As far as outreach goes, I know this is obviously one channel that's important, but what are your traditional outreach channels to
Well, for
access?
example, in Mexico, we do a lot of outreach to the general population in fairs, in any kind of gathering, public gathering, in the university, in associations like yours of different conditions. So this is the kind of things that we do. And also we do a lot of teaching in schools about neurodevelopmental disorders, and we tell them how we take tissue, animal tissue, and sometimes some human tissue to teach them, to show them the tissue, and we explain them why it's important to donate. So we do at different levels.
And once you have a donation and obviously the medical records, are you looking at autism spectrum disorder as a whole, or if they have a specific diagnosis within that, then you're categorizing?
More than the diagnosis itself, we are looking at the symptomatology. Because the problem with autism is really, I always like to say that it's not one conditions, but it's many under the same name. So like each case is different. It's not so much like we do Fragile X. Fragile X is a mutation in a single gene. So it's all the patients are more similar. But in autism, there is such a variety of symptoms. A person can be very functional, or can be not functional, or not verbal, or not social at all. So to me, when there is such a difference in the level of symptoms, it's like a different thing that you are studying. So more than for diagnosis, we look at the diagnosis, of course, but we mainly look at the different type of symptoms, specific symptoms, sub-symptoms, and the level of them. We pay special attention to intellectual disability, to epilepsy, because a lot of cases with autism goes with epilepsy are some of the symptoms that we are interested in.
Okay, wow. Thank you so much. That's wonderful. We really appreciate your time coming on today, and
Thank
we
you.
look forward to talking again soon. Thank you.
you.
Bye-bye.
Thank you. Bye.